Okay, let's get started. What we're looking at today is the sum of an arithmetic sequence. So last week we looked at an arithmetic sequence. If you remember, we move along an arithmetic sequence by adding a constant difference. Today we're going to look at adding them all up and finding the sum of an arithmetic sequence, also known as an arithmetic series. So you've had a little bit of a look at this investigation here. I'm just going to go through this for you. So what we're trying to do in this is we're going to try and add together all of the terms in a very simple arithmetic sequence. We have an arithmetic sequence here that starts off at 1 and it increases and has a common difference of plus 1 every time. So we're going up here by plus 1. We're adding together the first 100 terms in this sequence. So if we take the first 100 terms in the sequence, we are going to get 1 plus 2 plus 3 plus 4 plus ... So this ellipsis here in the middle, this means that there are other terms that we're not showing. And typically you can figure out what those terms might be, up to 97, and then 98, 99, and 100. So we're adding all of the first 100 terms. I'm going to try and figure out how much that will come to. Now our strategy for this is we are going to take another equation. We're going to take another equation which still is the first sum of the first 100 terms, but counting backwards. So we're going to have the last term first, 100, then 99, and so on all the way down. Now the reason we do this is if you take 1 and you add 100, what do we get? Well, we get 101. If you take 2 and 99 and add them together, what do we get? And if we take 3 and 98, add them together, what do we get? So taking all of the 100 terms in this sequence and adding the first term to the last term, we are always going to get 101. So if we take both of these two equations and add them together, well, we have the sum of 100 terms plus the sum of the 100 terms. So we get 2 lots of the sum of 100 terms. And then here we are going to get 101 plus 101 all the way to the end. There are going to be 100 lots of this. There's going to be 100 lots of this. So that means that 2 lots of the sum that we're after is equal to 100 times 101. So the sum that we're after, therefore, is going to be this sum of 100 terms, which will be 100 plus 100 times 101, all divided by 2. We can just divide the 2 across. We can take this 2 down to the other side through division. And that gives us 5,050. All right, so we're going to continue on with that. So in question number 2, we want to find let me just do it here. For question number 2, we want to find the sum of 100 terms, this time starting off at 3. And then we want to add 5, we want to add 7. Now, this sequence here, we need to find out what the 100th term in the sequence is. Well, in order to do that, we need to figure out what the common difference is. What is the common difference? Plus 2. So what would the formula for UN be? What's the first term in the sequence? 3. 3
plus 100 minus 1 times
2. N minus 1 times 2. So to find the 100th term, 3 plus 100 minus 1 times 2. That's 3 plus 99 times 2. What is 99 times 2? So we'll get 3 plus 198. 3 plus 198 is how much? 201. All right, so we found the 100th term in our sequence. So this is going to be plus ... What are the two terms that come before it? If that's the 100th term, what's the 99th term and the 98th term? 199 and 197. So we're going to go up to 197 plus 199 plus 201. So that's the sum of 100 terms. Now, if we write the sum backwards, what will the first term be? 201 plus 199 plus 197 plus ... plus 753. So adding the two equations together, we get, so if I take these two equations and I add them together, we get two lots of the sum of 100 terms. What's 3 plus 201? 204. 5 plus 199? 7 plus 197? How many lots of 204 do we have? How many lots of 204 will we have? 100. We'll have 100 lots of 204. So the sum of 100 terms in this sequence is going to be 100 times 204 divided by 2. And if we put that into our calculator, do we get the number given here? Try it on your calculator now. Try it on your calculator now. Yes, we do. We get 10. Okay. Yes, we are trying to figure out where the formula comes from. That's what this part of the lesson is, to conceptually understand where the formula comes from and why. We're doing a little investigation, we'll do a proof, and then we'll use the formula. All right, so for part 3, we're asked to look at a new sequence now. We go from 1 to 148. We need to show that the sequence has 50 terms. So in order to do that, we do need to find a formula for this sequence here. What is the common difference? Plus 3. And then what is the formula for UN? 1. N minus 1 times 3. So let's have a go at this question. It says, show that the sequence has 50 terms. So we cannot use 50 in this show that question. What we can do is we can use the formula we just made. So for A, we can take, what is the last term in the sequence? The last term in the sequence is 148. So we can take 148, set it equal to our formula, which was 1 plus n minus 1 times 3. Let's n solve this, or solve it. Solve this equation. Solve this equation. me just come around and see how people get on. Where's your calculator? Come on, guys. You know what calculator each. You don't just want to sit there. Go ahead on your calculator, solve it. Find out how we so passive in the afternoons.
It was 50.
Okay, so if we rearrange this one, we get 147 is equal to n minus 1 times 3. If we divide both sides by 3, we get 49 equals n minus 1. So n equals 50. There are 50 terms in this sequence. Find the sum of the 50 terms. So we go from 1 up by 3 to 148. So in B, we want this time to find the sum of 50 terms. We go 1 plus 4 plus 7 plus ... 148. We do our special trick of taking the first 50 terms, adding them together. We're going to get something looking like this. So 2 lots of 50 terms will be equal to what? 149, yeah? 149. How many lots of 149 do we have? 50. So the sum of 50 terms will be 50 times 149 divided by 2. Put that into our calculator. What do we get there? $3,725. All right. So before we move on, let's look at this one. We've done a couple of these now. Where does this number come from? Where does this number come from? The number of terms in the sequence? Where does this number come from? So let me take Simon. Which two equations? What do you mean by that? So let's not use the word equation. Let's use term. Which terms do we add? Not the second one. That would be 5. Could we also add this one? This is the last term. So if we wanted to find the sum of n terms, how many terms in the sequence would there be if there's n terms in the sequence? N. This number here is U1 plus UN, the first and the last term. And then we divide it by 2. So this is the formula for counting for any sequence now. If we wish to find the sum of n terms, we have n times, or you can rewrite this sometimes as n over 2 times U1 plus UN, where U1 is the first term and UN is the last term. Let's say we don't know what the last term is. How can we find it? Well, we can take this formula, n over 2, U1, and instead of UN, we can put in the formula for UN. What is the formula for the nth term in a sequence? So if we simplify this a little bit, what can we do? We can open up that bracket inside. How many U1s do we have? So we have 2 U1s plus n minus 1 d. Now the formula is just in terms of U1, n, and d. So we have two formulas for counting the sum of m terms in an arithmetic sequence. This one's easy to remember, and if you have your sequence written out, it's very easy to use. First and last term times by the number of terms. It's actually the average. So if we look at this one here, it's actually n lots of the average of U1, U first and last term. So you're finding the middle of the sequence. It's n lots of whatever's in the middle of the sequence. Whether this is a term or whether it's just halfway between, depending on if it's an odd number of terms or an even number of terms. So this is the average of the sequence, or the middle. So you've got that formula, very easy to remember and to use. And then this formula, which sometimes is easier because you don't have to have the last term. You can just have the first, the number of terms, and the common difference. So if you had a sequence that looks like, let's say we knew it went 2, 4, 6, ... and you had to find the first 20 terms in this sequence, you could use the formula at the bottom there. That formula would very easily, you could find out what it's going to be. So it would be 20 over 2 plus 2 times 2 plus 20 minus 1 times by the common difference, which is also 2. A lot of 2's there. That's a great sequence. All right, that's me basically running through this. Here are our two formulas. This is the formulas that we see for the arithmetic sequence in the formula sheet. So we have the one that we saw last week, which is the nth term in a geometric sequence. And then we have the formula for the sum, the two formulas for the sum. Missing a little bracket there. Oh, missing a little bracket there. I find it easiest to remember the one on the right. I find this one fairly easy to remember. The other one, you can just see it on the formula sheet. Okay, let's have a go at using it. I'd like you to have a go at this problem for yourself. Give you 3 minutes for this. All right, so we've got a couple of questions here. Calculate the sum of the first 20 terms in the series given here. So we need to find our formula. What is our common difference? Minus 3. So let's use our formula. Our formula is the sum of, let me just copy the formula down in general terms. The sum n is equal to n over 2 u1 plus un, which is also n over 2 2u1 plus n minus 1 lots of d. So we need the sum of the first 20, which is going to be 20 over 2. 2 lots of u1, which is 60, plus 20 minus 1 lots of d, which is negative 3. That's 10 times 120 plus 19 times negative 3. Do we get 630? Excellent. Okay, so 2a. Find the sum of the arithmetic sequence given. So for this arithmetic sequence, we need to first find out how many what d is, and then find out how many terms there are. We're not told. So what is the common difference that we're seeing here? Plus 4. And then the last term in the sequence is going to be 90. So we need 90 is equal to, and the first term is negative 10. First term plus n minus 1, lots of d, and d is 4. This means n is equal to how much? Let me just work it out. N 90, so it's 100, it's 25, 26. So now we need to find the sum of 26 terms. And we can use the 26 over 2. The first term in the sequence is given, and we also have the last term in the sequence. So it's possibly a little quicker to use this formula, which is going to give us 26 lots of, we're going to get 26 lots of 40. 40 is in the middle of this. So 26 times 40. 1,040. Let's try B. So find the least number of terms that must be added to the series. That's the one that's given. To obtain a sum greater than 100. So we need to find out how many terms are going to be in our sequence. We want our sum is going to be 26, it's going to be n over 2 minus 10 plus 90 has to be bigger than 100. So 80, or no, let's do it, 40 n has to be bigger than 100. So n has to be bigger than 10 over 4. N has to be bigger than 5 over 2. N has to be bigger than 2.5. Ooh, something's gone badly wrong. Sorry, did it have to be? I can clearly see that 3 terms is not going to be giving us a sum greater than 100. All right, let's have a look. I've made a bit of a huge error here in this one. So I'm trying to figure out how many terms in the sequence so that the sum is greater than 100. But the formula that I'm using, I can't use this version of the formula, because this version of the formula assumes we have 26 terms in the sequence, like the one above. That's where it's going wrong. I have to I don't know what the last term in the sequence is when I don't know how many terms are in the sequence. So I've made a bit of an error here on this one. I have to use the other formula. Yeah, I have to use the other formula. So we need 2 times U1, which is negative 10, plus n minus 1 lots of our common difference, which is 4. This has to be greater than 100. So let's put it in as an equation and solve for n.
So what do we make the equation equal to?
100. Let me do it here on my screen. Sorry?
Why 100?
Because it says in the question, so it wants the sum to be greater than 100. So we need to put this into our nsolve, algebra nsolve, and we need n over 2 times negative 20 plus n minus 1 lots of, what's our common difference? 4. Needs to be equal to 100. We solve for n. So when you try this and you solve for n, we get a negative number. So what can we do to fix this problem? We need this to be a positive number. So we have to put in comma 0, comma, obviously there's going to be less than 100 terms. And then we get 10.7. So our first solution for this is that n has to be greater than 10.7. Now n can't be 10.7. It has to be a whole number. So it's going to give us n is equal to 11. Now on nsolve on this one, we can see that my first answer was n is equal to minus 4.68, because if you remember, nsolve always gives you the answer closest to 0, but they can't be negative for this one, so you have to put in your bounds and say look between 0 and 100, because we know that n has to be greater than or equal to 1 for an arithmetic sequence. Okay, some tricky ones there. We're going to look next at sigma notation and series. It's a way of writing different types of terms. So a geometric sequence or a series like the one that we're adding up all the numbers from u1 up to un. And we can write it using the ellipsis notation as we've seen here. We can also write it using the sigma notation. Now the way that this works is we have this symbol here, sigma, which is for a sum. We start with this lowercase I1. I is our iterative variable, so I1 is the first term in the sequence. That's this one. So I is going to start off at being 1. Then it's going to keep going bigger and bigger, 1, 2, 3, until it gets all the way up to n. And that's how sigma notation works. So it's the sum of all ui from I1 up to in. Let me show you how you can use a few. So if we have this written here, what does this mean? Adam? We have this mathematical notation here. What we're going to do is we're going to take I. I is going to have a few different numbers. What's the first value I will have? 1. The first value I will have is here, 1. What's the next value it will have? I will be 1, 2, 3, and this tells us when to stop. So what we're going to get here is we're going to get 2 times 1, 2 times 2, 2 times 3, 2 times 4. So this is going to give us the numbers 2, 4, 6, 8, which is 20. Let's have a go at some questions for this one. So, example 15. We have to write the number from 1, so the sum of all the terms from 1 to 4 of the expression 2i plus 3. What's the first value I will take?
1.
So we have 2 times 1 plus 3. What's the next term in the sequence? It's going to be 2 times 2 plus 3. What will the next term in the sequence be? Yep. Ooh. Where did I go? And the next term in the sequence? Are there any more terms in the sequence? No. Why not? Because we have this 4 at the top that tells us when to stop. So that's going to give us 5 as our first term. What's the second term in the sequence?
7.
The third term?
9.
And the last term?
12.
11. Notice that this is an arithmetic sequence because this is linear. This is a linear term here, which generates an arithmetic sequence. What's our common difference in this sequence here?
2.
We're going up by plus 2. So the first term in the sequence is 2 plus 3. That's this. And the common difference is this. So you can quite easily see in an arithmetic sequence in its linear form when you're writing a sum like this one. All right.
Sir?
Yeah.
When we do the notation kind of the sigma and we go from 1 to 4 like we're doing here, are we always going 1, 2, 3, 4?
Yeah.
It's always
Yeah. You always iterate it. That's why we use the letter I here. You know, in math we often have certain letters of the alphabet for certain purposes. We use A, B, and C for constants, X and Y for variables. If we need a third variable, we use Z. We use F for functions, then H, G. We use N for integer. We use I for iterative integers, ones that go 1, 2, 3, 4. So I, J, K we use for that purpose. You use them in subscripts often, like in this particular case, or a subscript in a matrix and things. It helps you understand how the variable's being used. Okay, so B, calculate the sum of these terms. So in order to calculate the sum of these terms, it's good to identify what your first term is and what your common difference is. So in B, if we want to find the sum from I equal 1 up to 4 of the expression 2i plus 3, we can convert it into an arithmetic sum. So there are 4 terms in our sequence. Our first term in the sequence is 5, so we need 2 lots of that. And then we need n minus 1, which is 4 minus 1 lots of d. So that's 2 times, that's 10, plus 3 times 2. And we have 2 times 16, so 32. Let's check this using our calculator now. So So take your calculator in your hand. Follow me through on this one. Take your calculator out. Switch it on. We're going to press menu. Then it comes under calculus. And see number 3 is sum. Click that one. You should get your sigma symbol, and we can type it in as we see it here. I. Yeah. So there inside the bracket you want 2 times I plus 3. We should get, what number do we get? 32. Okay. All right, last example for today. Our last example is to write the series for this one using sigma notation. So, what type of series is this? How do you know it's arithmetic? It goes up by the same number. We have a constant difference of plus 2. What is the first term in the sequence?
1.
So U1 equals 1 and D equals 2. Now if you remember when we did it last time, we need one in the form of A n plus B. We need one in this form. Well, A is always your common difference. So this one is always A. And your first term is always A plus B. Now, if we know that A is equal to 2, we've got 2 times n plus B. Sorry, we've got 2 plus B is equal to the first term in the sequence. So I'm using the formula A plus B equals U1. So what's the value of B going to be?
-1.
B equals -1. So if we wish to write this series using sigma notation, capital sigma, start from 1. How many terms in the sequence? 6 terms in the sequence. And our formula?
2i minus 1.
2i minus 1. Excellent, Talia. Excellent. Okay, this is how we write this using sigma notation. Have a go at exercise 5K now in class.